Hello everyone. So this video is about sequential circuits in Verilog. Last time we have done conventional circuits in Verilog. This time we'll talk about sequential circuits in Verilog, and I will show you state machines. We'll talk about state machines towards the end of the video. So here we will compare sequential circuits with combinational circuits here. So in sequential circuits, what we have is memory element. We will save the output of the combinational circuit. After that, we have to use what we have saved in order to compute a new value of output. Okay, so the combinational circuit will give us outputs. That output will be saved here in the memory element in the next clock. When the time passes, this is a time reference for circuits. That value will be saved. The value that we have saved will be used to compute a new value of output. So this combinational circuit looks for inputs that come from here and from here, from memory element and from input, and it computes a new value output, and it saves some output so that it can be used next time. So the other important thing in sequential circuits are it uses clock. So clock is used. What is clock? Clock is a square wave that we have done in lab 3, a square wave that is used as a reference for circuits. So that's how they understand circuits. So circuits understand time using clock. So the reference of time for humans, it's easy to understand time, yeah, because biologically we know how time works, we know how the time progresses, but for circuits it's very difficult to understand. So they know time by the reference of clock. So they say when the clock is rising from 0 to 1, do something. Whenever the clock is rising from 0 to 1, do something. Or when it's falling from 1 to 0, do something. Okay? Or when it is 0, do something. When it is 1, do something. So there are 4 types of things that the clock is used. One is when the clock is rising, when it's changing from 0 to 1. That is when I do something. That's when I save something here, for example. And when it's falling from 1 to 0, that's the second one. The other one is when it is at 1, it could be here, it could be here, it could be here, anywhere. Or when it is 0, it could be anything between here. So in our FPGA designing in Verilog, we use a positive edge. Positive edge means when the clock is rising from 0 to 1. That means when the voltage is rising from 0 to 5 volt. Okay, when it's changing from 0 to 1, that is when we save something. That is when our circuit is triggered, activated. Okay, so that's how the clock is used. One clock is composed of 2 parts, the high part and the low part. So one clock cycle starts from low, from 0, and it goes halfway and it rises and stays there. So the length of this time and the length of this time is the same. Okay, half of the time is 0, half of the time it's 1. So sequential circuits, they use clock to understand time and to synchronize between the combinational circuit and the memory element, because combinational circuits doesn't use clock, so they just change whenever input is changing, the output changes immediately. It doesn't need to wait for rising edge or falling edge. It doesn't need to wait for anything because there's time here. It doesn't wait for anything here for clock. So combinational circuit doesn't wait for anything, but using clock we synchronize the memory element and combinational circuit. So this guy will do its job whenever the clock is rising. So it has to prepare any value that we save before the clock is rising, before the clock is going up. So I will explain a little bit more with the next slide about this. But for now, let's understand that a clock is used in sequential circuits and it's used to refer and understand time and it's also used to synchronize between combinational and memory elements, sequential circuit. So in total, this is a sequential circuit. It has a combinational part and it has memory element. It saves what is output of combinational part. This is what you need to understand for now. The next slide. So this part, this is the combinational part. This is where you do any logic things. This is where you do the logic stuffs. For example, you could say if input is like this, then give me output like this. So the decisions are made in this part. After this is done, this is our registers. These are two flip-flops. So flip-flops, when they come together, they make register. So this is like a register now. So we save values so that we can use them later after a clock, after one clock. So this guy decides and prepares value to be stored just before the clock rises. Just before, at this time, it has to be ready. And when the clock rises up, it will be saved. Okay? So this guy takes inputs from here and from the memory and calculates the output to be stored and to be outputted to the external world. What to store, what to output is decided in the combinational part. These guys are just storing, doing nothing else. They just store. Flip-flops, they store whenever clock is coming, they store. So the next slide will explain more. Here we can consider the flip-flops as switches. Whenever the clock comes, whenever this clock comes, and the rising edge comes, the switch is closed. So 1 will pass here, 0 will pass here. Whatever value we have here, it's ready before the clock is rising. That time it will pass. This will close, it will pass. So this time you are looking at this one, this part, and when I make next, see, this part is rising. At this time, it's very short time. Time is in this side. So at this very short time, it's very short, it closes for a very short time and it passes the values from the left side to the right side. So that's why we say it is stored. It's in the memory now. So from this time until this time, the logic have time to compute a new value to be stored again. It will compute a new value until here. Okay, so this is stored now. Let's go to the next clock. The next clock, until this part comes, a new value is prepared here. The decision here made is it's your decision. You can do anything. You can do anything here. It's your logic. You can decide anything. But that decision resulted like any value 1 1 now. So just before the rising edge, a new value is prepared. That new value will pass here when it's rising edge. So the rising edge will come here in the next slide. Here it is. So this very short time, the value has passed. So in this way, we save values and that value is used again here before the next trigger, before the next rising edge, pause edge. We call it pause edge. It's a rising edge. Okay, so that is how sequential circuits work. They have combinational part that does the decisions between the stored element and input, and it provides us what to store and what to output. So the stored values are dependent on the clock, and everything that is done here has to be ready before the pause edge. Okay, when pause edge comes, it's saving it. Okay. So here I will talk about state machine. What is a state machine? State machine is a way to describe any system. It describes any system in finite number of states. Finite number of states. So it cannot be many, like it has to be finite. It has to be finite. For example, here I have LED. You could think of it as a lamp if you want. A lamp, a light. So this light could be on or off. What else could it be? It can only be in two states. In one of the two states. It could be on, it could be off. Nothing else. There is no in between. So we have finite number of states here. Two states. Okay, we have two states. In state 1 is on when the light is on, the LED. Off is when the LED is off. So we use input button, push button to control or to jump from one state to another state. To make the light on, we push button. For example, right now I'm on state. The light is on. I want to make it off. So I press button. When button is number, it's 1. So the state will be changed. The light will go off. Right now it's off. So when it's off, if I press nothing, if the button is 0, or if I didn't press, then it will stay there. It will go back to itself. At this stage, light is off. If when I'm at this stage, at off state, when button is pressed, then I will go to on. LED is on, output is on, output is 1 right now. LED is 1, LED is off here. When I'm here and the LED is not pressed, when button is 0, then it will go back to itself. So this is what state machine is, and shortly this is how it's done. And the next slide I will explain how to do state machine using code. And here I have two types of doing the state machine in our Verilog codes. So this is using if. I'm just showing you the inner part of the combinational part. It has sequential and combinational part. This is a combinational part of it. Okay, I will show you in the code, but for now we have if state is 0. If state is 0, then LED will be 0. At state 0, this is off state, LED will be 0. That means LED is 0. And if when I'm at state 0, if I push the button, that is button equals to 1, then state has to go to 1, which is I have to go here in the next clock. So state next means the next. This is something that has to be saved, and state is something that's coming from the memory. And this is what I'm sending to the memory. This is the output of the decision, the combinational logic. This is output of the memory. This is going to the memory. This is coming from the memory. This is coming from the memory. Okay. So this is off state. This is on state. So here you could have said like else if button is 0, 0, then state next should be 0. But since we are in state 0, there's no need to write it, but you can write it. It's okay. You can write it. Same thing happens here. So this is using if else. The other way is using case. So same thing, state is coming here. Then I have one state here, I have another state here. So they are coming, the state value is coming, and then I will decide here. I have if inside here. And the difference is I'm using case here, case structure. The other one is using if structure. Nothing difference. So this is the case, this is the state 0, state 1, everything's done here. I think this is very straightforward, but I will explain more in the code. Okay, let's go to the code. This is what we have, and this is my code. This is an example code. I will explain more here, and I have a test bench also. I have a test bench to test my system by giving inputs. So my state machine has two sections here. So these inputs are very straightforward. I have clock and reset. Reset is just to reset all the values that I have there to 0. Resetting is just for formality. LED is the output that I want to show. State and state next are internal registers. They are just internal. I'm not showing them outside. That's why they are red here. Internal. LED next is also internal because it's used there. The output that I'm showing out is what I'm seeing here. LED is the one that's going out. Okay, so the major things, the very important thing that you have to see here is that I have two sections always, posage clock and there's always at star. This is the combinational part of my code. It goes until here. This is combinational part of my code, combinational logic, and this is my memory element. This is what I'm saving. So anything that I get from the combinational part has to be led next, and I will save that into my led. It will be saved here when posage is coming. So this part and this part, the whole part, this combinational part, are working in parallel. They are working in parallel, okay, because they are always always blocks. They are parallel. So this part is triggered by posage clock. Whenever clock is rising from 0 to 1, it is triggered. It does its job one by one when it's triggered, when the clock is rising from 0 to 1. What about this? What is the trigger of this? It is triggered by star. What is star? Star means all the sensitivity of this block. This block is sensitive to state. If state is changing, then this whole block has to be redone again. It has to be recalculated again. So anything that you see on the right side, or anything that you see inside a case or reset, all are listed here. So I could have listed them in this way. I could have listed them in this way if you want. I could have listed them in this way. What else do I have? Reset. I have reset here. So I will say reset. All of them I could have put them inside here. Button, I will put button also here. But the easiest way to do is just put star. That means all the sensitivities are put here. So whenever one of them is changed, then this part has to be recalculated again. It has to be recalculated. Okay. So after that I have this part. So for formality, you have to reset all the registers that you have before you begin to do anything. So this resets all the values. State next and let next has to be resetted. So reset has to be 1. So in the test bench, in the beginning, I will put reset to 1 initial. I'll put reset to 1. After that, that input will go to my module, to my design, and reset the values to 0. All of the registers, my flip-flops, my registers are set to 0 here. After that, I will do all my part inside the else block. Inside else. If reset is not 1, then do the job. This is the job where it's done. So state is here. If state is 0, then output is 0 because I'm in off. The lamp is off. If button is pressed to 1, then the state has to go to 1. Otherwise, it will stay there. So you could have written else. You could have written something like this. Else go to 0. You could have said something like this. But it's the same thing. So you can forget this one. Okay. So the other section is 1, and this goes like that. So state is 1, then the output is 1, the light is on. If button is pressed, then the state has to go to 0, to off state. Okay, so this is how the state is working. So whenever the state next is given a value, it gets value from here, yeah, from the logic part. So that logic part, when the clock comes, this guy, the combinational part, has finished its job and prepared a new value for us. State next and let next value are ready before the clock comes. So when the posage comes, those values, let next and state next, will be saved. This is the part where we do saving. This will be saved. Exactly, just like I explained from the slide. It will be saved here. So this is what is done, and I could have done this in a different manner. How do I do it? Using if. So I have it here. So I could have done this using if. Okay, I will remove this one just for explanation, and not that one, this one. So I could have done this using if, just same thing. State if state is 0, do something. So I could have done this in this manner, but for now I chose this one to explain. So they all work same. You can try it if you want. So I'll just go back to where I was before, and let's run this thing. Okay, this is my design. My design is clear. I will be simulating this. So my simulation, my test bench is here. My test bench has prepared register values, clock. It has to generate clock and feed to my state machine, because my state machine needs clock because it's a sequential circuit. And reset, it needs reset. It needs also input button to decide whether to go from one state to another state. So I have to generate a clock here. So this one is generating. So this is 5 nanosecond delay. It means hashtag 5 means generating 5 nanosecond delay. Okay, so clock is rising from 0 to 1 in 5 milliseconds, 5 nanoseconds. So this is a clock that is 5 in total. It's 10 nanosecond period. 10 nanosecond period clock is generated in this part. Okay, this is just to give input to our clock. So here we feed our state machine unit under test a clock. We feed it a clock, we feed the reset, and this is like calling a function. It's called instantiation. We have done this part here, and output is also here. After that, we feed inputs. This is where it starts. So this is at time 0, clock is 0 at time 0, and reset is at 1 because we have to reset everything in the beginning, and button is 0 in the beginning. So after a couple of times, this is 10 nanosecond, 100 nanosecond, and reset is set to 0. So if reset is 0, then I can do my state machine work, because if reset is 1, then we do resetting, but now reset is 0, so we can do the job. So button is given 1 value. So if our state was 0, then it has to go to 1, and output has to be 1, yeah. And the button is also set to 0, and it's the 1. So this is just for trying our state machine. We give inputs here. Okay, we give it 10 here because we think it works in that way. Okay, so let's bring this one into a simulation. This is simulation now. Okay, so in simulation I can see it here. Let's run it. Let's run state machine. Let's synthesize it if it works fine. Okay, as we can see, it works fine. This is warning. Let's go to warning and see. It says delay is ignored for synthesis. Yeah, delay is used for synthesis. It's here. Delay is here. The delay is here. This is for simulation purpose. For a synthesis, it's ignored. So it's okay. Everything is okay now. We can go to simulation and select our test bench and run it and see how it works. Okay, so this is what we have. As we can see our output, clock, reset, and input button, but we can't see our state. So I want to see my state. So I have to go to click here, expand it, UUT, which is unit under test, go to state, and drag and drop here. When you drag and drop and relaunch again, there's no need to save. Here you can see the states changing here. Let's make it bigger. Okay, so our state is here. So we are in state 0 and we get input. We are in state 0, the beginning state 0. After some time, reset is 1. So after resetting everything, after that we set it to 0, and we start giving inputs. Button is now 1, and we are in state 0. So when we are in state 0 and button is 1, what do? It goes to state 1, yeah. So this is state 1. After a clock, it goes to state 1. So state is converted to 1 because we are in 1. After that, we are in state 1. We are in state 1 and button is 1. button is 1. After a clock, this is a clock. After 1 clock, this is 1 clock. After 1 clock, we are in state 1 and input is still 1, so we have to go back. State 1, input is 1. What happens? We go to state 0. We go to state 0, equals to state 0. Same thing happens. We are in state 0 and our input is 1. We go to state 0, to state 1. It changes like that because input is 1. Okay. Here, when state is 1 and the input is 0, we do nothing and it keeps on going like that. Here we are in state 0 and we state 1 and input is 1, then the next state has to be 1. I mean, it has to be 0. Okay, and the output, the LED, we can see it here because it's active after 1 clock. We can see it here. So this is the state and this is the output. After 1 clock, we see the effect after 1 clock. Same thing here, same thing here, same thing here. Okay, we see the effect after 1 clock. So this is how you simulate the design, and we have done this. It gives the same result if you use the if and case, and state machines work in this way. And thank you for watching.